All right, we're taking notes on solutions and solubility, especially polar versus non-polar solutions. We're going to talk about what those are. Our first note, though, on our coding notes is what is a solution anyways? And it's a mixture of multiple substances. It's a mixture when those multiple substances are uniformly mixed together. When I say uniformly, I mean like totally smoothly. You cannot tell where one stops and the other starts. They're perfectly smoothly, uniformly mixed together. Uniformly mixed together. Okay, just a preview as we go forward. I'm going to be doing a lot of those things that college professors do, like saying a bunch of information that explains this while not writing it down. So you all need to be on your best game here by catching the stuff that I'm dropping, even if I'm not specifically writing it, right? Just a forewarning. Okay. A mixture of multiple substances uniformly mixed together. Did I say that a solution had to be liquid?
No.
Most solutions that we deal with in chemistry class are liquid, but there's tons that aren't. For instance, the air that we're in, is the air a mixture?
Yes.
Yeah, we got nitrogen and oxygen and other stuff. Can you tell where the oxygen stops and the nitrogen starts? It's uniformly mixed. The air is a solution of gases. That's interesting. Andy?
So if it's a solid, isn't it a compound?
Oh, interesting.
Yeah, Andy.
Can there be solids that are solutions? Okay, here's the key. If they're mixed perfectly together, but not chemically bonded together. So if you've got two solids and you combine them and they chemically bond, then it's a compound. You're right. But what if you have, for instance, tin and copper, and you take the copper and the tin and you put it into a certain chemical solution, and you get that very hot, and you make the tin atoms move their way in between the copper atoms and evenly distribute throughout that material, but without chemically bonding. Then you would have an alloy. That's a metal, it's a solid metal, but it's actually a solution. Bronze is a solution. Brass, you've seen like brass doornail stuff? Brass? Yeah? Anybody?
So what about a smoothie? That's a solution.
A smoothie! Oh! Is it perfectly uniform?
No.
You can see bits, right? Yeah. Also, you might have a mixture of like, some of it's like the frozen part, and some of it's the liquid part. You blended it up so much that you can't really tell the difference. But if we look closely, we'll be like, oh, okay, that's one little crystal of ice, and it's next to a little liquid part here. Also, you get into some interesting properties of things called colloids or colloidal fluids. Like people like to ask me about like ice cream or Jell-O, and it's like certain chemicals, like certain compounds, that start to behave. They behave kind of sort of like solids, kind of sort of like liquids. Anyways, solutions can be gas. You can have gas solutions. Obviously, you can have liquid solutions, right? Salt dissolved in water. It's a solution of salt water. And then you can also have solid solutions. Very, very interesting. Okay, there's two parts of the solution that we need to know about that we're going to give names to. Two parts. Part number one is going to be the solute, and as Emma mentioned earlier, I've already talked about it. That's whatever you have less of. The solute is whichever you have less of. The solute dissolves into the solvent, we would say. The flip side of that, the other part that we'll need, is something called the solvent, which I already mentioned. The solvent is whatever we have more of. And I would say the solvent dissolves the solute.
Word solute is like
dissolve into the word solvent.
Yeah.
How do you measure if there's more or less of something?
Well, you just have to know. So if you made the solution, you would know.
Okay, but I mean, like, you say whatever's less of, do you measure like with volume?
It's usually by mass. So grams. Kilograms, but usually grams.
You're saying like the solvent would be the water, the solute would be the salt.
Got it.
Alright.
Yeah, you got it. The most common solvent that we're going to use is going to be water. We also used another solvent today in lab. We used isopropyl alcohol too. You'll see solvents, you'll see water usually as the solvent in chemistry, but other things can be used. Has anyone ever wondered, like, how does salt actually dissolve? Like, what really happens? I've wondered that, and so I looked it up. But first, Blaine has a question. Hit it.
What if like in an alloy, like the two metals, there's an equal number
Oh boy.
of like, which one would be which?
I don't know. I guess once they cross that line, then the names would switch. But they're exactly equal?
Yeah.
I don't have an answer, man.
Like there's 5 grams of whatever and 5 grams of.
I get what you're saying. I don't have an answer. Here we go. We're going to look at what actually happens when salt dissolves into water. Okay, we're going to get down to the nitty gritty, like the atom scale. I looked right at atom when I said atom scale. That was unintentional. Okay, so I've got a beaker of water. In the water, we've got our little water molecules. You recognize them? Our little Mickey Mouse dudes. I'm going to just kind of blow it up a little bit here, just make it a little larger so we can see it. We got an oxygen atom here, and then attached to the oxygen, we should have 2 hydrogen. Yeah. Oh boy. Okay, I got to tell you a little secret about oxygen. Oxygen is greedy. It's very, very greedy. It really likes to steal electrons. It's very aggressive about getting its own electrons. It is that kid at the lunch table that's like, sure, I'll share that bag of chips with you. 3 for me, 1 for you, 3 for me, 1 for you. That's oxygen. It's sharing electrons with the hydrogen, but it's an uneven share. The electrons spend more time around the oxygen. Wait. What's the charge on an electron? Positive or negative?
Negative.
So if the electrons are spending more time by the oxygen, what overall charge does that oxygen end up carrying? A little bit of a negative zone over here. There's more electrons. The hydrogen, meanwhile, it's got a proton down in the center, right? What's the charge on a proton? That electron that should be balancing it out is spending more time down here, so it's kind of exposing that proton. And so you end up with a positive charge on that end of the water molecule. This makes the water molecule polar. Polar means it has a positive side and a negative side. Water molecules are polar molecules. Oh, look at that, we got 2 of them now. Oh no, they're duplicating.
I wonder how.
Right? Okay, now here's the cool thing about polar water molecules. You've got a positive side and a negative side, right? Which side is going to be attracted to which? Are they going to attract negative to negative?
No.
No, the magnetic attraction is going to flip them around in the water solution, and it's going to be like, bing, and then this one's going to be like, bing, I'm right attached to there, and they're going to, as they're flowing on each other, they're going to be making these little sort of momentary connections, and it's like a momentary, it's not a full bond, it's actually called a hydrogen bond. It's a momentary attraction. It can break real quick and like, boop, float away, and a new one can come in, but they're always making these attractions to each other. Have you ever noticed how water likes to bead up into a circle? Yeah. This is water. Each water molecule is trying to grab onto every other water molecule around it. And so they're always pulling in towards each other. I know, right? In space, what shape do you think a water drop makes?
Circle.
Perfect sphere. Here on Earth, gravity's like flattening them down, right? But they're always trying to fight that and bead back up on each other. Okay, that's fine, that's cool, whatever, Mr. Butter. Here's what that has to do with dissolving. We've got our salt crystal. Do you remember how salt is an ionic compound?
Yeah.
That means that they've like totally given an electron away, right? Somebody else has lost an electron, somebody got one. That's gonna give each atom in there a charge. So like this one has a negative charge, that one has a positive charge, positive charge, negative, and it's like this kind of perfect opposite situation where they're all attracted to each other. Remember this? Like a month ago? Waters have little charges too. And so as the waters flow around this salt crystal, each water molecule will actually come in, and there's like all that wiggling going on because everything's vibrating, and they'll come in and they'll actually like pop one of the atoms off, and they'll pull it off with their magnetism. And they'll wiggle in between, and they will slowly or quickly, depending on what it is, they will pull these molecules out, and you can see that's our negative charge one, and the positive sides of the waters are towards it. This is our positive one, and the negative sides of the water are towards it. And they will surround that atom from the salt with six. It always happens to be 6 water molecules around each atom because of 3-dimensional shapes. That's the angles that they can get in at. This water is not permanently attracted to that atom. It will vibrate out of there and a new one will take its place. It's kind of this like rotating system. Everything's flowing. But once that atom has been pulled off the salt crystal and surrounded by water, it now behaves like water. It's part of the water solution. It flows. Light can pass through it. It's water. But it's water with salt dissolved in. How about that? That's kind of cool, huh? So then once you boil the water off, the water molecules would leave, and these salt crystals would gather together and form a new crystal. Okay, cool. That's that.